So now we start a new chapter. Students might find it easier. It's really more mathematical than mechanical. You'll see. It's all about solving differential equations, basically. So if you look at the spring system, so I have it horizontal like this, with the mass m at the end of the spring of distance k, and then say here is the equilibrium position, and then you measure the extension with respect to that position. You know that the mass always, well, vertically will be subject to its weight, and then maybe I didn't draw it, but maybe there's like a smooth surface sustaining the motion, so there'll be a reaction compensating this. But otherwise, horizontally, it's only subject to the force of the spring, the restoring force. So we've done that before. You know that you end up with what's called the simple harmonic motion equation. And then there are some terms that I've introduced before. How do you characterize this equation? It's an equation whose unknown is a function, not x, a number, but x of t, a function of time. So it's not an algebraic equation, it's a functional equation, but it involves x and the derivative of x, so it's a differential equation. The highest order of differentiation is 2 here, x double dot means x double prime means d2x dt squared. Highest order is 2, so you call it a second order ordinary differential equation. That's all okay and easy to understand. What's harder to grasp maybe is the concept of linearity for an equation, for a differential equation. Just think of, for you, linear means y equals ax plus p, right? Ax plus p, that's linear. A is a constant, just multiply x, x is by itself, b is a constant, x plus b, that's a linear variation. You get a line if you do y, if you draw y as a function of x. And then you have the same concept for functions as well. Is this expression linear in x? And when you say x, you also mean x and its derivatives. Right? If you have y equals ax squared plus bx plus c, then it's not a line anymore, it's a parabola. Similarly, here, if I had x squared, for instance, it wouldn't be linear in x. That's why I write here. Every term and its derivative appear at most to the power 1. Or it could be 0 right here, the x dot doesn't appear. It's either 0 or 1. And not only that, but they appear by themselves. Right? I wrote that into quotes here. By themselves, it means linear. If I had, if I had, for instance, cos of x, that's not linear either. Right? So students will say, well, but x appears by itself. But no, it's not x, it's cosine of x. It's a function of x, so it's not linear. Or if I had x dot, you might think, oh, x appears by itself, x. No, but they multiply by one by another, so it's quadratic in x. While when we say x, we mean x and its derivatives. So all of those are nonlinear terms. They make equations almost impossible to solve in most cases. Sometimes you can remember we did the logistic equation that had p squared in it. We managed to solve it. Most of the time, you just can't do any progress. You have to turn to numerics mostly. But here, in this course, 90% of the equations are linear, and this one is linear. And linear is great because you could just have general theorems, general solutions, everything can be solved in all generality. Okay. In particular, you know, the fact that it's linear tells you that a linear combination of the solutions is also a solution. Right? If I have two solutions, x1 and x2, and then I do what's called a linear combination, x1 I know that cosine sine were the solution. A linear combination means you just multiply one solution by an infinite, any arbitrary constant you want, you multiply the other by any other arbitrary constant you want. So you have a sort of double infinity of solution. That's a linear combination. Well, it's also a solution. That's easy to prove. I don't want to write it. But you can see that if I differentiate this twice, blah, 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 I get it. Okay? So I'm just going fast through this. But that's something to know. Linearity is good. Yeah. Because if you find a solution, you in fact have an infinity of solution. If you find two solutions, you have two infinities of solution. Another thing to note is that if you have a second order differential equation, you'll have two arbitrary constants. And that's always the case. And you can figure out why. Because you're integrating, so when you integrate once, your solution is up to an arbitrary constant, and then you have to integrate twice to get the final solution. So you'll have a second arbitrary constant. They appear multiplying, yes. So every differential equation has two, every second order differential equation has two arbitrary constant of integration. But if it's a linear differential equation, then it's now still here as multiplying coefficients. And then we saw, if you now go back to mechanics or to physics, that those two that are arbitrary, usually you fix them because you have a problem, a real world problem at hand. Usually you're given the initial position and the initial velocity, but it could be something else, maybe the initial acceleration, whatever. In any case, you will be given two conditions, and so by applying those two conditions, you will find the two constants. You will adjust the two constants to satisfy the two conditions, right? And we saw that in the first chapter. Okay, so that's it for my introduction to second order differential equations. Let's talk about complex algebra now. You've seen that before, I hope. Yeah, the leaving cert. Let's go the other way around now. If I look at a function, I can ask myself, what kind of differential equation does this function satisfy? Let's look at this. Exponential of RT, function of t. If I do the first derivative, get ERT, that's the chain rule. If I differentiate again, I'm going to get R is going to come down again. So I get R squared RT, ERT. And then I can see, I can combine this to find the second order differential equation that X satisfies. I have to stop this. Here. ERT solution am I right? I can see here that X double dot is R squared ERT, and that's R squared X. Yeah, because ERT is X. So there you go. I found an equation satisfied by this here. Now, what if just for fun, I was taking xt omega t, where I square root of -1. Have you seen this, the imaginary number? Yes, I have to assume you have. But you've seen it. Did you? Did you do the leaving cert?
Well, I came from the States. I'm not sure if it's the same.
But did you do complex numbers?
Yeah.
Oh, okay.
I know it.
Everybody knows complex numbers. Yeah. So now if I want to differentiate this, it's the same. The same is going to apply. I bring down the coefficient in front of t. If I differentiate it twice, I have I omega squared I omega t, and I omega squared is I squared omega squared, and I squared is -1. Huh. It just works. What do I get? That omega t is solution to this equation. The simple harmonic motion equation. Question?
Will it always have that layout, the second root plus a constant times x? Is that always like the usual layout?
For the simple harmonic equation. That's the simple harmonic equation, yeah. That's the most general form of the simple harmonic equation. That's not the simple harmonic equation. But that is. Nice. That's the most general form, yeah. If there was other terms, it would be called something else. And in fact, we want to see slight variations of this equation in this course, in this chapter. Yeah. So, if that solution of the simple harmonic equation, and we've seen the most general of simple harmonic equation, it follows that this function here must be written in this form. And that's right. It must be, because we saw in the first chapter that this was the most general solution to this. So there must be 1a and 1b, since this particular solution is such that this is true. And let's find them. Let's find the a and the b. If I write it at 0, I get exponential 0. That's 1 on the left, and on the right I get a times cosine 0, which is 1, plus b times sine 0, which is 0. And so I found that a is 1. What about x dot? Yeah, I can differentiate the left, I can differentiate the right-hand side. Derivative of cos is minus sine, and there's the chain rule in there. Derivative of sine is cos, and there's the chain rule in there too. If I write it at 0, what do I get? I omega on the left, because exponential 0 is 1. And on the right, I get b omega. B is I. What did I just prove? Cos omega t. And that's valid for any t, so I could write it like this. For all theta. Isn't that a nice way to prove that formula? That's the so-called Euler formula. We did it using differential equations. Yeah, I just called theta, omega t, I called it theta. And then it works. Since t is arbitrary. That's the so-called Euler's formula. Nice. What if I put minus theta instead of theta? What if I say theta equals minus x if you want? I'm going to have cos minus theta, but cos is even, so it stays like this. And then I have plus I sine of minus theta. Sine of minus theta is minus sine of theta. Yeah. And now, okay, so I went a bit fast here, but if you put cos minus theta, you get cos. If you put sine minus theta, you get minus sine theta. And then if I add those two equations, I'm going to get rid of the sine theta part. Ah! It feels like. Anybody want to see The Invisible Man? Only one person?
Again.
Two. Ah, what do you think?
No, I didn't see it.
Didn't like it?
Okay.
Rubbish.
It just seemed.
Didn't do it for you.
It was like a demon.
What? It's so scary. So tense. What did you think?
I couldn't see the point of the main character.
The main character.
I couldn't even see the main character.
Oh, the Invisible Man is there. Ah, good point. I thought it was very good. It shouldn't have been called the Invisible Man, and then it would have been even more terrifying. I thought, yeah. It's all about gaslighting, really. She says it's happening to her, nobody believes her. Okay. Oh, I made a mistake. Yeah. If I add the 2, I get rid of the sine. If I subtract, I get rid of the cos. But I have 2i, right? So I have 2i over 2i. So these are nice formulas. Another thing you could do for any n, instead of theta, you could write n theta. And then that's the same as this, right? Exponential to the power a times b is exponential to the power a whole lot to the power b. And then this, I have it from there. And this, I have it from there as well with n theta instead of theta. So I end up on the left, cos n theta I sine n theta, and on the right, and what do I have here? But the Moivre. Nobody knows how to say that. But it's in the book. De Moivre, I guess he was French. Oh, I didn't bring the book. But it's in the book, yeah. You've used it for the leading soil. Remember that formula? Easy to prove. And the book is just given to you just like that. You say, where is that coming from? That's where it's coming from. You could do all sorts of applications of this. For instance, I could ask myself, what's the implication of this equality, this identity here? Yeah. Exponential of a plus b is exponential a times exponential b. If I write each of those terms using my formula above, my Euler formula, have cos theta plus phi plus I sine theta plus phi on the left, and then on the right,
Is that simple?
is it what, sorry?
That's simple, like theta plus, what's that simple?
Phi.
Pi or phi?
Phi. The capital is this. And sometimes, in fact, there's two ways of writing phi. You can write like this or like that. So on the left, I have this. On the right, I have cos theta plus I sine theta times cos phi I sine phi. And then I can expand cos theta cos phi plus I cos theta sine phi. I'm just expanding plus I sine theta cos phi plus I times I. That's going to be minus 1. Right? And then if I have a complex number on the left, that part here is called the real part. This part here, that's in factor of I, is called the imaginary part. Have you seen those terms before? Then I can identify the real part on the left with the real part on the right, and the imaginary part on the left with the imaginary part on the right. These are two separate. They live in two separate spaces, I guess. And you could just say real parts must be equal. So that's going to give me on the left cos theta plus 5, and on the right cos theta cos phi. And then the imaginary part, like my girlfriend, which is a minus 100. No, square root of minus 100, sorry. The imaginary part, sine theta plus phi, is cos theta sine phi. So there you go. We've just proven all those formulas, those trigonometric formulas that are given to you without any explanation. They're very easy to prove using Euler formula. In the logbook, you have, of course, A plus B. Maybe I should have used A plus B. But you have those formulas afterwards. That's where they come from. Or that's how you could prove them, if you wanted to. Yeah, what about proving this here? If I write de Moivre's formula when n is 2, on the left I'll have cos 2 theta plus I sine 2 theta, and on the right I'll have cos theta plus I sine theta squared, which I can expand as cos squared theta plus 2I cos theta sine theta plus I squared. That's going to be minus sine squared theta. Yeah, I just wrote the de Moivre formula here when n equals 2. And here I have a squared, so I just do a squared plus 2ab plus b squared. And now I have a complex number on the left, complex number on the right. I'm just going to identify the real part and then the imaginary part to end up with cos 2 theta theta minus sine squared theta and sine 2 theta equals 2 cos theta sine theta. Another set of trigonometric identities that you might have wondered where they came from. Yes, another way to do it is just to put phi equals theta into this, and you land up with the same. But not direct. There are many ways. Another thing we could do, if I take theta is pi, I end up with, I take theta in pi is pi into Euler's formula, I'll have cos pi, which is 1, minus 1, sorry, plus I sine pi, which is 0. And so I end up ei pi equals minus 1. And that's the famous Euler identity. Nice formula that brings together E, I, and pi. Okay. Time for a break. Okay. So, now, let's go back to simple harmonic motion. If the spring is the mass is just moving at the end of the spring with no friction, it's fine. That's simple harmonic motion. But what if there's a little bit of friction? Remember, we've seen that earlier. You have to add a damping term like this. If you add this into the equation on the right-hand side, you divide across by m. You have k over m, that's omega squared. And now you have a modified equation. That's called, it's like the simple harmonic equation, but with one term in it. So that's called the damped simple harmonic motion equation. And how do we solve it? We just go the same way as we did earlier. You look for a solution. Just take a wild guess. You reckon this might work. Yeah, I don't know why I wrote this here. And I'm just going to put it in, right? I have x dot is going to be r e r t. X double dot is going to be r squared e r t. I substitute into the equation. I see I can divide across by ERT, and I end up with a quadratic. And then I know how to solve that. I know it's going to be minus b plus or minus p squared minus 4 omega squared over 2. And then I know that the roots are real or repeated or complex depending on the sign of b squared minus 4 omega. And then for each of those cases, whether it's 0, positive or negative, I'll have a different type of root, and so I'll have a different type of solution. That's what I'll show you in the next lecture, which will take place virtually tomorrow. So,